finally, this is the elaboration of the micro-automata project. So, as it says here, automata are self-operating machines that typically consist of a clockwork statue or scene and were first created centuries ago in Europe and Asia. In many ways, they were the direct ancestor of what became electromechanical robots. Many modern toys use electric motors to achieve movement, but they still rely upon gears and other principles of simple machines. For our purposes, the automaton is a good way to explore the machine's function of converting one form of energy and motion to another. They are also a way to teach simple mechanical problem-solving skills. So, right, automata is plural, in case you were wondering what this A versus the ON deal is. And then automaton, or automaton, would be the singular. We've talked a little bit about how you can take rotary motion and convert it into linear motion as that thing goes up and down, right? So that would be this conversion of energy, or really of one type of motion to another, right? And think about a lot of toys that people have today. They are just kind of different versions of that, right? You think about like your, I don't know, the chattering teeth that you like wind up and then they chatter across the desk, or like wind back cars that you wind, go backwards and let go, and they go forward much faster. All these kinds of like toys have little mechanisms in them that allow them to do these things, right? We call those simple machines or compound machines if there are a few simple machines put together. The bottom circle inside the plastic cup on the crank is referred to as a cam. Right, that's the one going through your axle or crankshaft, whatever you call that. A cam is a mechanical linkage that transforms rotary motion into linear motion or vice versa. A car engine is a familiar machine that converts the up and down reciprocating motions of the pistons to rotary motion to drive the car's wheels. All right, you think about pistons in a car, right? If you got a V engine, it's like this. All right, and they're going dong, 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 like that. All right, as they do that, they're actually spinning a shaft, which eventually connects to the axle. I don't know how cars work exactly, but eventually does connect to the axle and spins it, right? So for this automaton, using a cam that grips the other circle well, higher friction coefficient results in a more efficient machine and less mechanical energy lost. Think about if I had you use paper maybe instead of cardboard for that cam. It might just slip, right? There are times where we typically think of friction as bad, but there are times when friction is needed. Otherwise, the mechanism won't work the way we want. All right. The handle is a type of crank that utilizes torque. Torque is the tendency of a force to rotate an object around an axis. All right. You calculate torque in the same way you calculate work. All right. It's force times distance. Torque is directly proportional to the product of the force applied. So that's the force. And the length, the distance, of the lever arm, which is the distance between the axis and point of force application, right? If we didn't use a handle, the automaton would be more difficult to turn. I talked about that briefly in the last video, right? If you're trying to pinch it with your fingers, it'd be more difficult to turn for a few reasons. One of which, though, is you can create less torque, right? By getting a crank handle that gets you further away from the middle of that axle, you actually need less torque or you need less effort to turn the axle. So think about it like this. If a door swinging on its hinges is an example of this, try to open a door where you normally would, all right? Then crack the door so it's not locked, all right, or latched, and then try to open it like this says, pushing very close to the hinges. All right, what's going to be more difficult? Well, it's the one close to the hinges. Just try it out, see how it works. That is an example of torque in action. All right. They also mention the handle itself, right? Can be an example. So it should be easier for you to turn. Think if you have like a handle, like the kind the velociraptors can turn in Jurassic Park, right? That should be easier to turn than a doorknob, right? Which, let's be real here, if we had doorknobs in Jurassic Park, we wouldn't have to worry about the raptors coming through and getting us. So thank you. That is the end of this video and lessons on the micro-automata.